Have you ever wondered how your computer's operating system works? It's like a city's infrastructure, unseen yet indispensable. At its core, an operating system, or OS, is a software that manages hardware resources while also providing services for applications. It's the bridge that connects user applications and the hardware of a computer system. Think of the OS as a team. It has a leader, the kernel, which interacts directly with the system hardware. It's responsible for task management, memory management, and device input and output. The kernel is the first to boot up when you start your computer and stays active throughout. Then there are system libraries, which provide ready-made solutions for common tasks. System utilities, on the other hand, are like the OS's toolkit, providing essential services like file management and network configuration. And let's not forget device drivers, the interpreters between the OS and hardware devices, and the user interface, which allows you to interact with your computer. But what makes up an operating system? Let's delve deeper into its components. At the heart of every operating system is the kernel. This is the core component, the real powerhouse. It's entrusted with the low-level management of hardware resources, providing the essential services that keep the system ticking. Picture the kernel as a diligent maestro. It's conducting a complex symphony of tasks, from process scheduling to memory management, device I/O, and file system access. The kernel is the one shaking hands with the hardware, making sure everything runs smoothly. It's the first thing loaded into memory when you boot up your system, and it stays there, working tirelessly throughout the system's operation. But the kernel doesn't work alone. It's part of a larger team, each member with its own critical role. There are system libraries, system utilities, device drivers, and the user interface, each contributing to the seamless functioning of your operating system. So the kernel is the core, but there are other components that help it do its job. System libraries, the bridge between applications and the operating system. Now, what are system libraries? Simply put, they are collections of reusable code and functions that applications can utilize. They serve as a kind of translator, providing higher-level abstractions and services to applications. This means they turn complex low-level hardware interactions into simpler, more manageable tasks for applications. Let's consider some examples to understand this better. Imagine you're developing a program that needs to read and write files. Instead of wrestling with intricate hardware details, you can simply use functions provided by a file I/O library. Similarly, networking libraries handle the complexities of network communication, allowing developers to focus on their application logic. If you're designing a graphical user interface, graphical toolkits come to your rescue, providing pre-made elements like buttons, windows, and menus. In essence, system libraries are like a toolbox, filled with useful tools that make software development more streamlined and efficient. Now that we've explored system libraries, let's move on to system utilities. System utilities, the tools for system management and administration. These are command line tools and utilities that the operating system provides for a range of tasks, from managing files, configuring network settings, to monitoring system performance and troubleshooting issues. System utilities are the go-to tools. Let's take file management tools as an example. Commands like ls, cp, and mv are commonly used to list, copy, and move files respectively. They provide an efficient way to handle files and directories. Then we have process management tools such as ps and top, which are essential for viewing and controlling the running processes. Network configuration tools like ifconfig and ip are indispensable for setting up and managing network interfaces. These utilities, while often overlooked, form the backbone of system administration, making the complex tasks manageable and the mundane tasks automated. From managing files to monitoring system performance, system utilities cover a wide range. Next, let's learn about device drivers. Device drivers, facilitating communication between the OS and hardware devices. Now, imagine trying to use your computer without a monitor, keyboard, or mouse. It's practically impossible, right? This is where device drivers come into play. They are the unsung heroes of the operating system, bridging the gap between the software and the hardware. Picture device drivers as interpreters who can speak both computer and hardware. They control and utilize peripherals such as your printer, graphics card, network adapter, and storage devices. But here's the catch. Every device speaks a different language, and it's the job of the device driver to understand and translate these languages for the operating system. The beauty of device drivers lies in their ability to abstract hardware-specific details. They provide a standardized interface, allowing the operating system to communicate with a myriad of devices without needing to know the intricate details of each one's inner workings. Device drivers ensure smooth interaction between the OS and hardware. Now, let's move to the user interface. User interface, the gateway for users to interact with the operating system and applications. It's like the front door to a house, inviting us in to explore and utilize the services inside. Now, there are two main types of user interfaces: command line interfaces, or CLIs, and graphical user interfaces, known as GUIs. In a CLI, users enter text commands to perform tasks. It's like speaking a secret language with your computer. On the other hand, a GUI presents a visual environment with windows, icons, menus, and buttons, making it more intuitive and user-friendly. But what makes up these interfaces? Well, UI components include shell interpreters, which process our commands, window managers that control the look and feel of our screens, and desktop environments that provide a complete user experience. In essence, the user interface is our bridge to the digital world, allowing us to communicate and interact with the operating system. UI makes interaction with the OS possible, but where does all our data go? Let's explore the file system. File system, the organizer of data on storage devices. This is the mechanism that arranges how data is stored and retrieved on your storage devices such as hard drives, SSDs, and flash drives. You can think of it as the library catalog of your computer's data, keeping track of where everything is stored. The file system provides a hierarchical structure, allowing us to organize files and directories in a user-friendly manner. It also offers functions for creating, reading, writing, and deleting files, essentially handling all the interactions with your stored data. There's a variety of file systems out there. For example, you have FAT and NTFS predominantly used by Windows, ext4 commonly found in Linux, and APFS used by Apple's macOS. Each has its own unique features and performance characteristics, but they all serve the same fundamental purpose: to manage the way your data is stored and accessed. The file system keeps our data structured. Now, onto our final component, process management. Process management, the overseer of executing programs. In the realm of operating systems, process management is like a maestro conducting an orchestra. It's responsible for creating, scheduling, and terminating processes, ensuring that the symphony of executing programs plays harmoniously. You might be wondering, what exactly is a process? Simply put, a process is an instance of an executing program. It's the active entity that's using system resources like CPU time, memory, and I/O devices. Now let's delve into some key components of process management. The first one is the process control block, also known as PCB. Think of the PCB as the ID card of a process. It holds all the information about a process: its current state, the position of the instruction being executed, and even the resources it's using. The operating system uses this information to manage and schedule processes effectively. Speaking of scheduling, that brings us to our next key component: process scheduling algorithms. These algorithms determine the order in which processes are executed. They play a crucial role in ensuring that all processes get a fair share of the CPU's time. There are various types of scheduling algorithms, each with its own strengths and weaknesses. Some prioritize short, quick tasks, while others favor longer, more intensive ones. The choice of scheduling algorithm can greatly influence the system's performance and responsiveness. As you can see, process management is a complex and essential part of an operating system. It's like a juggler, constantly keeping multiple processes in the air, ensuring none of them drop. It's responsible for managing the life cycle of processes, from their creation to their termination, and everything in between. And there you have it. Process management ensures smooth execution of programs. That concludes our journey into the structure of an operating system. So, we've explored the structure of an operating system from the kernel to process management. We've learned that the kernel is the heart of an operating system, directly interacting with hardware and managing essential tasks. System libraries, on the other hand, are treasure troves of reusable code, providing higher-level services to applications. We've also delved into system utilities, those invaluable tools that allow us to manage files, monitor performance, and troubleshoot issues. We've discovered the role of device drivers, the vital software components that facilitate communication between the operating system and our hardware devices. We've navigated through the user interface, the gateway through which we interact with our computers. We've also understood the role of the file system, organizing and storing our data, and process management, overseeing the life cycle of processes. Understanding these components gives us a clearer picture of how our computers function every day. Thanks for joining in on this exploration of operating systems.